At Envision, we implement our distributed locks using Redis. And a distributed lock is just a lock that has to be honored across a set of horizontally scaled ColdFusion pods. And as far as implementation goes, we implement our distributed lock using simple keys with a TTL or a time to live. So let's look at Redis here with a key that would represent a distributed lock. And we can see right now that there's no lock that exists. Furthermore, if we do a TTL on that, we can see it's a -2, which means that lock doesn't currently exist. Nothing's holding that lock open. So let's just jump over here and let's initiate a lock. And we can see now that it has a TTL of 59 seconds. And we can see if we get the value, it's just a simple string value saying dynamic Redis lock. Now, this lock has already expired in the background, or rather I should say that the work has been done and the lock has been released. So if we get the lock, it'll say nil. And if we do TTL of -2, meaning that the lock doesn't exist, the key doesn't exist. Now, with short-lived locks, usually everything just runs smoothly. But if we have a very long-running lock, typically what we'll do is we'll hold that lock open with a long TTL or a long time to live. However, if the pod that has that lock held open crashes or has to be rescheduled by Kubernetes or is on a pod that was revoked because it was a spot instance in AWS, suddenly we might have an open lock and there's no process that's ever going to close it explicitly, which means that the lock will be maintained open until the TTL or the time to live runs its course. So to try and hedge against that, I wanted to experiment with this idea that we could have a distributed lock, which is what we just saw in the Redis there, that has a short TTL, but has a TTL that can be dynamically extended during the lifetime of the synchronized algorithm. So here in this demo, what we're saying is I want to obtain a dynamic lock, and the fact that it's dynamic means that it's going to obtain a Redis key based on this unique name, and then my work operator is going to be invoked with this extend lock function. The extend lock function takes an arbitrary number of seconds and will extend the lifetime or the TTL of the underlying Redis key by that number of seconds. So by default, this key is going to be allocated with a 60-second TTL, and then during it, I'm going to continue extending the TTL of that Redis key by 2 seconds. And then I'm going to simulate long-running work with the sleep command, also 2 seconds. So essentially, this is going to run 5 times inside the dynamic distributed lock. And it's going to, for each iteration here, pause for 2 seconds and then extend the timeout of the underlying Redis key for 2 seconds. So what we should see is that this sleep and this extended lock more or less cancel each other out, and the TTL of this lock should remain fairly constant during the execution of the demo. So if let's just prepare a system here. So let me make sure I have the right TTL. Okay, so now if we kick off the task here and we jump over and we just start pinging this, you can see that as time passes, the TTL of this distributed lock basically stays around 58, 59, 60 seconds until the demo completes, at which point it explicitly revokes the distributed lock, which kills the underlying key, which means the distributed lock can now be opened or obtained by other processes. So let's take a look at how this works. So if we jump down to the dynamic lock function, you'll see that it's actually a shorthand for a slightly larger function that takes a configuration as opposed to simple arguments. At this point in the demo, really the only additional configuration option here is the initial TTL of the Redis key. So if we jump down to this version, here we can see we have the config. It has the name of the distributed lock, the operator, that's the passed in closure that defines the work to be done during the distributed lock. Let's just jump down here again. So under the hood, I then grab the TTL in seconds, but then I also calculate this lock expires at, which is an epoch seconds at which the key should be expired. Now, our initial set, which we'll see in a second, is going to use the simple TTL, but then as we push out the duration of the distributed lock, it's just easier to use the epoch seconds. So we want to calculate that as well. So basically, the algorithm runs in 3 steps. Step 1 is obtaining the lock itself. So here you can see I'm going to the Redis pool. I'm getting a Redis resource from the Redis pool. That gives me Redis. I'm then attempting to set the lock key, but only with the NX flavor. The NX here indicates that the key should only be set if it does not already exist. If it does already exist, it means that another process currently has the distributed lock held open, and therefore we can't open it ourselves. So the NX says only set this if it doesn't already exist. Then the EX here says that we want this key to have a TTL of this value, and this is the TTL in seconds, which, as we saw above, is going to default to 60 seconds. All right, if this returned a null result, then it means that we could not set the key, which meant that another process already had the distributed lock held open. So we're just going to throw an error and say that we could not obtain the dynamic lock. If we did have a non-null value, it means that our process was able to obtain the lock, which means that we move on to step 2, invoking the actual lock operator. That's the closure or function that defines the distributed task work, the distributed lock work. So here we're going to invoke the lock operator, but you'll see that we have to pass in that extend lock function, which pushes out the TTL of the underlying Redis key. And the extend lock function is itself just a closure here. You can see we're going back to the Redis pool. We're adding the additional time in seconds to that expires at. So if you remember here at the top, we have both the initial TTL, but then we also have this epoch seconds expires at. So when we extend the lock key, all we're doing is adding that number of seconds to the epoch seconds, and then we're going back to Redis and telling it to expire this particular lock name at this particular point in the future. So the underlying operation can continue to call extend lock as many times as it wants during the lifetime of the distributed lock, and it'll just keep getting pushed out. Now that I'm saying this, we probably do run into a tricky situation where you might actually call the expires at after the key's been revoked. That I think will actually just end up creating a new key with an empty value with a new expiration. But this is all about hedging edge cases against edge cases. Now, after the operator runs, we then move on to step 3, which is just releasing the lock. And all we have to do there is delete the underlying Redis key that represents the distributed lock, thereby allowing other processes to set that key, thereby obtaining the distributed lock. Now you notice that we have the final step inside of finally, because we don't want to depend on the lock operation to run successfully. It might have an error in it. It might have a syntax problem. It might do something that throws an error. We always want to make sure that we release that distributed lock under the hood. We want to always delete that Redis key. And there we go. So again, I talked about the edge case down below with hedging our bets. So the edge case is really that we want our distributed lock to have a TTL that's short enough that if this were to have a bug, or if the pod were to crash or to shut down and we didn't have an opportunity to delete our distributed lock key, we want that TTL to be short enough so that it doesn't block other processes from obtaining that lock for too long. But at the same time, we want it to be long enough so that the key still exists by the time we go to extend it for a subsequent period of the synchronized workflow. So it's not a perfect solution. It's just trying to take a problematic solution and make it more tenable, make it more viable as an approach to a distributed lock for long-running work. Ideally, long-running work should probably be broken out into its own sort of task queue where it can operate maybe outside the primary boundaries of the application, but that's a whole other conversation and requires a whole other level of effort. I'm trying to do the least amount of effort to make a bad situation worse, and I think this at least gives me a path forward where I can start to hedge against this idea that my pods on a Kubernetes system might get rescheduled, or my underlying spot instance may get revoked, and I might accidentally leave a distributed lock in place. And now, even if I do leave a distributed lock in place with this type of approach, it's only in place for a short period of time and won't end up blocking a system indefinitely, or at least for a really long period of time.